All right. So basically, your theoretical class is almost done. Now we want to apply the knowledge you got. We want to apply how to model using any software. Yesterday you learned how to write a code using MATLAB. Okay, and today I want to show you now just theoretically, okay, what the Ansys Fluent has, and in the afternoon we will show one problem. Okay, one of our tutors will show you step by step how to set up a model. Okay, but before I start, I want to make sure that I am not from Ansys. Okay, I am not promoting them, but because this software and this methodology, the finite volume technique, this software is actually any result produced from here, validated results, is now is accepted in the research community. Also, when you publish paper, they don't ask any question. So there are a lot of softwares now available, and we have the console multiphysics software nowadays. A lot of people are using. Especially, I found in India it is very popular. Okay, and that is they use the finite element method. We did not discuss about that here, and that software is called a multiphysics. So that is not only fluid mechanics, but also some other things like almost all physical problem you can use that software. But this the Ansys also they have a couple of things. They can also model the solid mechanics as well. Okay, and Ansys actually, when I did my PhD in 2005 to 2009, I used Fluent, okay, and the Fluent version was 6.3 or something. And this version, it was only just Fluent, not Ansys. And then that you need a mesh file to solve in that using that software, and you have to create geometry from some other places. Like we use Gambit. Gambit is another software, and we actually created the geometry, we created the mesh, and then we import the mesh into the Fluent. And after that is, I think it is in 2010 or 2011, the Ansys company, they actually took it from the Fluent. And then also Ansys, they have their own another software. It is called the CFX. Okay. So once you have the Ansys, you can see the CFX and the Fluent. Actually, they both can do the same job. I don't know why they capture it, because maybe the to overcome the competition. Okay, CFX and the Fluent. So they bought all together to do the monopoly business. Maybe, I don't know. But you can actually try both of them if you want. But some problems like dealing with the particles and those things, I think CFX is better than Fluent. But the problem we actually the theoretical things we already discussed here. Fluent, I think, is the best. Okay. So some of my slides is very much obvious. We already have discussed. So I'll skip. Okay. So you know what is fluid mechanics or fluid dynamics. So, but here we want to see that in the brief, the fluid flow can be solved or described by three basic physical law. Okay, it has more if we include some other things like the particles or other things, but this mainly the fluid flow. Okay, so that is the continuity equation where the mass is conserved. We already have discussed this morning, and the momentum equation is known as the Navier-Stokes equation. So that is based on the Newton's second law of motion. And the third one is the energy equation if you want to solve any temperature or some energy field. So mostly these three equations we'll be dealing with using the Ansys. So as in the morning you just learned that it is the Navier-Stokes equation is highly nonlinear differential equation, and it is not possible to get the exact solution. It's not possible at all. However, there is a millennium question. Okay, If you can solve this question, you will get $1 million US. Is already the declared. So you can see in the online somewhere. So people are actually trying to get the exact solution, especially from India. I found one professor, she is very close to the exact solution. So they are actually trying to solve the analytic solution. So, but still only the option is the numerical solution. Okay. So now there are 3 ways of solving problems. Yesterday, Professor Chakraborty explained. So one is called the analytical or the theoretical approach. Another one is the experimental approach, and the last one is the numerical approach. So before this computer was invented, there was no choice to do the numerical using a computer. But that time people used like analytical or some theoretical approach. Even in my master's, we actually did some analytical approach, and also in my PhD, half of my PhD is analytical, mathematical analysis. It's called the scaling analysis. Okay, the scaling analysis is a very, very nice way of solving a problem, and the result is very like correct to the same order of magnitude. It is not accurate because you have to exclude some term. For example, we mentioned that we have unsteady term, we have advection term, we have pressure gradient term, we have the viscous term. Okay. So during the flow development, unsteady flow development, in some stages, some terms are important and some terms are not important. For example, very initially, when T is very small, then the advection term is not important because the flow does not start. Mostly it is conduction is important. So that time we can ignore the advection term, and then we can use the unsteady term balance with the diffusion term. So this is the way we can actually get some solutions of velocity, some steady state time, or this kind of thing. So we mathematically, it's a very like a algebraic equation we got at the end, but it is very quick, and the result is very accurate to the 1 order of magnitude. And after that, we actually validated our result using after solving the full set of equations. Okay. So the second part is called the experimental approach. So experimental approach is very nice if you can do that, but sometimes it is very expensive. Especially one of my PhD students, he is working on the electrolysis. Okay, he is breaking water and getting hydrogen. So producing the hydrogen. So he is using the PEM technique in COMSOL, but the problem is he needs to do some experiment. But we cannot set up it. It's a huge expense. We cannot do that. So we are actually trying to get some data available in the research community, and then we want to validate our model. So that's why it is not always possible to do the experimental approach, and sometimes it is not possible to do the experiment. Okay? You cannot do the experiment if you want to do the lung research. You cannot take your lung out and do the experiment. Okay? So we have to do some other way. So the numerical approach, as you have seen that it is cheap in that sense that it only needs the computer, okay, and your knowledge of how to solve it. And this now computer is not very expensive; it's cheaper. So we can solve the problems. Although this is not very accurate, this is approximate solution, but it actually helps a lot. Okay. So if someone wants to build up something like an aircraft or something, so aircraft they actually started in 1960. Okay, they are actually using this on very badly the CFD because that help a lot. They have some idea, okay, how to design the machinery, how to do it. So they need some idea what will be the Mach number, maximum Mach number, and those kind of things. Though that's why they want to use this CFD, and it is very, very quick. Okay, so what is CFD? So you already know that the computational fluid dynamics is a set of numerical methods. Okay, So these numerical methods, a lot of methods that actually give us the approximate solution of the problems of like a fluid dynamics or the heat transfer. Okay. So the CFD is not a science itself; it's a tool. Okay, that actually help in different discipline to get the fluid flow or heat transfer, this kind of results. So the CFD solution are not exact. Then why not use the analytical approach? Okay, but as I said, it is not always possible to get the analytical or the exact solution. And experimental approach is more reliable, such as wind tunnel experiments. Then why not use experimental approach? So the answer is the CFD used because there are many engineering problems that can't be solved by analytical or experimental approach, and it is difficult to use analytical experimental approach. I already mentioned it. So difficulties like a theoretical approach and the experimental approach. So more here. So the approach gives exact solution, which is great advantage, but analytic solutions are only possible for limited number of problems or very simplified problems that I already mentioned, the scaling analysis. So we have to ignore some terms. Although we are ignoring, but it has some influence. Very initial time, it already trigger, okay, the buoyancy. So we should not completely ignore it, but we do it because of the to apply the theoretical approach. And experimental, as I said, the major challenge is the expense, and the other is the it has lot of uncertainties to actually do the experiment, because when you set up a numerical model, there is nothing that environment is influencing it. But if you want to do like some experimental setup, there are a lot of things affecting. For example, if you want to do some heat transfer, so your room should be exactly the same temperature. Okay, if it is like isothermal cases, but it is realistically it is not possible because always some heat transfer is happening. So we cannot actually set up very nice as like a numerical approach. A numerical approach, we can ideally give all the correct value. Now, CFD has some application, a lot of application. I think you can do everything in CFD, and especially for the aerodynamics of aircraft and vehicles, where we calculate the drag force and the lift force, and the power plant, the combustion of internal combustion engines and gas turbines, and the hydrodynamics of ships, and biomedical engineering. We will discuss about the blood flow through arteries or veins, and some environmental engineering is just distribution of pollutants that I'll give when I give my lung problem. I'll discuss about this one, the pollutants. So in a nutshell, CFD applied is almost every discipline of engineering problems, and from 1960s onward, aerospace industries has integrated CFD techniques in design and R&D and manufacturing of aircraft and the jet engines. So they are using for a long time. Now your own CFD coding and your commercial CFD codes. Okay. Yes, when I started doing my PhD, a lot of people actually told I'm using some black box and I have no idea about what is solving this system and this guys. There are so much negative until 2010, 2011. Lot of people, they are very negative about using the commercial software. Before that, as Professor Chakraborty told that he developed his own code and those kind of things. But after that, what happened is when you develop your own code, the geometry should be very simplified geometry. If it is a complex geometry like your lung tree, it is quite impossible using your own code. Okay, it's a very, very hard job. Like in your 3 to 4 years PhD, you have to use maybe 2 years or 3 years just to develop the code. and you'll get only 1 year to do the application. So, and this CFD code, like the commercial code, it tested by so many people all over the world. So that means this actually proved that it working perfectly. Or if it is your own code, maybe you can do some manipulation in your code, who knows, okay. So I think is reliability of using this software nowadays people actually realize, and now nobody will laugh if you use any these things. But you know, it depends. If you are a mathematician, most of the mathematician they actually develop the code. They like to develop the code, and that's why we are getting this kind of software, because behind this developing this software, a lot of mathematicians are working. They are actually developing codes, and they are helping for this one, and now we are using it. So it depends what is your goal, what you are going to do, okay. If you want to do like develop your own new methodology, new technique, then you can just work on the code development. But if you want to apply your code to apply some engineering problems, okay, and to understand the physics, so you can use this commercial software. So it actually depends. So problem solving using commercial package. So in the commercial package, we actually, it is, you know, very nicely organized because it is commercially. Otherwise, you won't buy it. Okay. So there are some free or the open source like software. Those are very good, like the Open Foam. They are very good, but they are not very user friendly. Okay. So, but they actually make very nice user friendly, and they put everything in one place. So what they have is, they have like a preprocessor, a solver, and a post processor. Everything is there. Okay. So initially you thought about which problem you are going to solve. You calculate, you find out what will be the boundary condition, what will be the initial condition, what will be the geometry. You just think about it. This is called a preprocessor. And then you put everything and put in the solver, and it is solving. But after it is solving, what you want to do? You need to present the results. So it is actually solving and storing data, all the nodal point. Okay, Professor already mentioned that in the node point. But if you want to get the result somewhere else, okay, in between nodes, so you need the interpolation. Okay, so that is the things that the post processing software can do that for you. So and Ansys Fluent or Ansys has its own CFD post. They call it CFD post. So you can do the post processing there, or some other people use like a tech plot or some other third party software. So you can also use it. And Fluent has its own post processing one, and Ansys has its own CFD post. There's a lot of way you can do it, but CFD post is very powerful, very, very nice. You can show a lot of things in there. So the preprocessor actually, this step includes the creating geometry and the mesh. Okay. So that's creating geometry and the mesh you can use somewhere else, and you can export the mesh and put in the solver. So this part is to numerically solve the fluid flow equations in the computational domain. Now the post processor, in these steps, results of simulation is analyzed and represented is usual form. So which one you like, the way your manager or your supervisor wants, you can actually present the result that way. So this is very nice tools. So the three method. So three method is mostly used. Okay. It is called the finite difference method. You already have learned what it is. And then the finite element method, which is not in this course, and the spectral method, not in this course. But the finite volume method actually the special case of finite difference method. Okay. So there are some special. And this finite element and spectral methods we are not using it. There are also other methods like LBM, lattice Boltzmann method, the mesh free particle methods. A lot of methods are available. So Ansys Fluent. So Ansys is an engineering simulation software. Okay. So, is a developer headquartered south of Pittsburgh in the South Point Business Park in, yeah. So, this is there where it is. So, Ansys Fluent is one of the most popular commercial CFD software package. So, we will use Ansys Fluent in this course to solve the engineering problem. Okay. So, the Ansys Fluent CFD solver based on the finite volume method, I already mentioned you. So, in the finite volume method, you know that the domain is discretized into a finite number of control volumes. Okay. So, the conservation equation of mass, the momentum and the energy if you have heat transfer related problem, and species if you have some diffusion problem. So, this kind of things are solved based on this control volume. So, now the steps in Ansys Fluent, what steps we want to follow here, and at first the pre-analysis. Okay. So, as I said, what kind of problem you are going to solve, what could be the initial and the boundary condition. So, if you have anything everything handy, then you do the create the geometry. Okay. Create the geometry, you can use any CAD software, but to use in that software in Ansys Fluent, I think you need to export the geometry into IGES format. Okay. So, start.IGES. So, this format you have to export, and then you can take it directly to the Fluent. And then you have to apply the mesh. Okay. So, Ansys has very nice meshing technique. So, there are three things in Ansys Fluent. Okay. Before you go to Fluent, there are in Ansys, you can say as a general. So, the geometry creation, we have the ICME, I think is ICEM, sorry, ICEM. So, you can create the geometry in ICEM, and then now we have, it's called Discovery something, right? There is newly they released another one, is called Ansys Discovery or something. So, that is a very close to the like the SolidWorks. Okay. You can actually create the geometry there, or you can use the Ansys' own geometry. There you can also do that. So, once you create the geometry, you just bring the geometry to mesh. Okay. And then you apply the mesh. So, mesh also has ICEM can give you, that is very good for the hexa mesh or rectangular mesh or square mesh. Okay, that is very good. But if you have very complex mesh like a tetrahedral mesh or some other mesh, I think the Ansys meshing system can do that. And after that, you need to do the physical setup. Okay, set up all the boundary conditions and like everything, like a model choose. There are a lot of models there. Which model you want to choose? Okay, because we discuss only the simple one. There are some other solver there and lot of other things as well. So, we'll show you when we, this afternoon we'll show you. We can show all the possibilities, and also Ansys Fluent give us a recommendation what kind of problem you should use which one. But you can do some testing, and then you can do the numerical solution, and after that do the verification and the validation. Okay. So, the best part of I like in Ansys is called the workbench. Workbench is like this kind of connections. They connect everything in one place. Okay. In Ansys workbench, you can just set up the circuit, and then from there you can just go for the geometry creation, finish the geometry, save it and come back, and then go for the meshing. The meshing can automatically get the geometry from there, and then you do the meshing. You just give all the boundary names, okay, and come back and then go to the Fluent. Fluent can automatically take the mesh file from there. You don't need to do anything. And if you want to do some optimization, so you can also do the optimization in there. So you can just, you need to set up which parameter you want to optimize. So just mention the parameters, and that can actually optimize you. And after that, if you want to do the post processing using CFD post, then click the CFD post. They can take all the results from the fluent you already calculated. So it's a fantastic way of doing using workbench. You don't need to like do all these components because all are separated, geometry is separate, then you can do meshing separate, and then you set up and then you run. All are actually separate files. But the Ansys workbench actually is connecting everything together. So it's a very nice tool. So yeah, the workbench looks like this. Okay. So it has see on the left side, it can actually do a lot of things. But I never use this thing. This is some of them only for solid mechanics. Okay. We need only the fluid flow fluent and the fluid flow CFX. So you can use either of these, both actually deal with the fluid. Okay. So once you click on the fluid flow fluent, it actually gives this circuit. Okay. Like a geometry, the mesh, the setup, solution, and the results. The results mean the CFD post. You will get everything in one place. Or the thing is that if you want to change anything anywhere, that actually influences everything. So if you are very smart, you can take some component, not the all of this here. There are some component in the. I think you have to go down. I could not show all here. So this geometry, mesh, setup, solution, all are different components. So you can just put on the geometry and then you can connect. Okay, you can connect geometry with the mesh in one, with the mesh other one, and the mesh on the third one. So you can put a lot of things together. If you change one, that will not alter your whole things. So if you want to show some parametric study, okay, the couple of mesh you want to do, so this kind of thing. So you can actually do that. We will show you when we this afternoon. Okay. So this will use this Ansys. Here is the tools of simulation using Ansys. You will use and control these tools from here. Okay. And here are all the tools you need for your simulation. So geometry, click the geometry, it will open up the geometry page, or if you do it in ICEM or the discovery, you can actually export. Right click and export the geometry. Okay. They will automatically open a new page. And then the mesh, then click mesh, it will open up the geometry. Or if you have your own mesh, you just directly go to the setup. Okay. When you go to the setup, you can import the mesh file if you have. Okay. And then go to the solution, and after that the results. So steps. So the pre-analysis, you want to solve a real world engineering problem numerically using Ansys Fluent. Then you will need the boundary condition. As I said, boundary condition is very important. If your boundary condition is not realistic, you will not get good results. You will not solving the realistic condition. So boundary condition is very accurately, you have to deal with it. Otherwise, your result is not like physically correct. So you observe that the real physical situation, or you will obtain data so that you can represent the actual case. Okay. So you will also obtain the corresponding theoretical or some experimental result, and then you can compare your results with them. So in our CFD research, what we do is for the validation, for example, we are solving one problem, totally new problem. So that problem is not solved yet, is not available. So how can you validate? So before you need to for the validation, so you have to actually get very similar or close to your problem. Maybe someone already did. Okay, just get their information and you just set up based on their data and get the results and then compare it. Once you compare means your solver, the solver issues and the setup you did is okay, is correct. Okay, that's the way we actually validate, because we don't, if somebody already have done and then we don't need to do it again. Okay, so you cannot exactly get some results already published and you compare your results. So what you have to do, you have to actually design something already available in the literature and then get some results and compare with them. Or if already available as an experimental data, so you do a numerical simulation based on the parameter they use, everything they use, and then compare your results. Okay. In that way, you can validate your model. So, a lot of way of the validation. And the Professor Chakraborty told that there is an upper limit and a lower limit of acceptance. So, if you want to know generally as a CFD researcher, what you do is generally if you compare our result with some numerical results, we just take the error like about 2% maximum. If the error is less than 2%, we accept. But if we compare our result with some experimental data, we can accept up to 10 to 15% error. Because as I told, the experimental is a very uncertainty there, because it has some other influence from the environment. So, we still we just accept it. And sometimes, for example, our research, my group is doing lung. So, everybody's lung are different. Then how can we validate our model? Even though if I take your CT scan now and after a certain time, two results will be different, because I don't know where your diaphragm is. Maybe your diaphragm coming here. So, you are taking different times, your geometry is different. So, there are a lot of issues previously from the reviewer. We get a lot of comments that how can you validate your model? It is not absolutely way of validating it. So, normally what you do, we just do not the very quantitatively, but qualitatively. Okay, it's just we calculate something, and already some people did, and we found that they are very like trained the same. Okay, trained the same. This is the way we just validate, and we do a lot of mesh dependent tests, so that our mesh or our grid is not affecting our results. Okay. So, I already have mentioned it, the geometry. You need to create the geometry either using your Ansys design modeler software, or you can some CAD software. Okay, and export that on as IGES format. And meshing is one of the most important step for your simulation, and the simulation result actually depend mesh quality. As I said, the more mesh you have, the better result you have, but we have to sometimes compromise, because we cannot use huge mesh. To solve our one lung problem, we use up to 30 million mesh. So, it takes about 1 month using 64 processor, 64 computer to solve one problem. It takes more than a month. So, sometimes it is not possible, not feasible. Okay. Now, then the physical setup. So, yeah, this is another important thing. So, Fluent already give some advice, which type of model, like a natural convection, what kind of solver you need to use. So, what kind of discretization you need to use. So, they already give some idea, or you can do by yourself, do different testing and these things. But remember, in CFD, good results depend on your experience. Okay, so do again, and then you will get your experience. What is the problem? Where is the problem? Then you can identify by yourself. Okay. So now, how to set it up? Just go to the Ansys workbench, and then the analysis systems, and then the Fluent. Just drag it, put it there, and drag it there, and then you can see the Fluent solver using this path. Fluent tree will appear. This looks like, though this tree actually showing all the steps you have to complete for a successful simulation. Okay. So, first one is this one. When you just come to the Fluent, when you click the workbench, okay, is open up this one. So, once it is open up, then you have to think about what dimension your geometry is. Is it 2D or a 3D? So, if you choose if it is a 2D and you are choosing 3D, you cannot read. So, your geometry, Fluent cannot read your geometry on your mesh file. So you have to choose correct one. But that one is, if you use workbench, that automatically they select, because they can recognize what is your geometry. If it is 2-dimensional, there it will be 2D select. And the double precision, and here you can tick or untick, it depends on you. So how much correct results you want. Professor told yesterday the truncation error and some other error. So this error is the precision error. That means after decimal places, how long you want to keep your result correct. So single position is 16 and double is 32. Okay. So 32 is the huge, and it takes a lot of space. The data file will be very big. Okay. And but generally I use this one because that will give you more accurate results, but it takes lot of your space. The file will be bigger. Okay. And now what you want to display here, displays the mesh after reading. So when you go up, give OK, that it can read your mesh file, and here you can show which one you want, just tick here. And now the processing options. Do you want to use the serial or parallel computing? Okay. So here you have to choose. If it is serial, that is one processor will solve your problem. So nowadays the computer has 8 core, 4 core. Okay. So you can, even in your single computer, you can use the parallel. You can use 4 or you can use 8 or something from here. So that they can solve it very fast, faster than the serial. Okay. So here you have specify your solver about your geometry, 2D or 3D, and the accuracy 1, like the tick, the double precision or the single precision, which one you want, and then unmark the double precision marks if your solver is single one, or you just mark it for the, either see the 16-bit floating points, or double precision is giving 32-bit floating points. So the processing options are to speed up your simulation and using full power of your cluster computer. So you can use 1 core, or you can use some computer has some 8 cores. So you can just select which one you want, or you can do some testing. Because during my PhD, my supervisor was very angry on me because I am using the maximum number of core, and then he said that you need to do some testing. So which one is optimized? You know, sometimes parallel computing, if you use more processor, sometimes it will slow down because it's called the message passing. So one processor will pass the message to the other one. So it takes some time. Okay. So if you use more processor, it takes some time to pass the results, because it is called the domain decomposition. So they are dividing the domain and solving one processor this part, other processor this part, and they are exchanging the value. So to exchange the value, it takes some time. For example, maybe 4 processor is good for you, but if you use 8 processor, it takes time for this message passing and it slow down your this thing. So in that way, he just told me, do like simulate 10 iteration and see your real time how much it takes for single processor, then double processor how much time it takes, and draw a curve, and then curve is converged. Take this one. Okay, this how many processor you need. So that is very important. So it is not always good to use like a maximum number of CPU. Okay, so this is the fluent. When you read a mesh file, it looks like that. Okay, looks like this. So the geometry, they show the mesh here. Okay, and they will give all the information here. All the information, especially the mesh, all the mesh information you can see from here. Okay, so you have to check very carefully that the volume of the mesh is not negative. So there are sometimes if you have some error, it can give you some negative. So we have to check it. And all the left panel, you have to like choose for the solver and what kind of discretization you need to use, everything on the left side. So you have to do it. Okay. So some of those things are very straightforward, and some of these are not very straightforward. In that case, for example, like your boundary condition, if you want to give like some value like a temperature, like for example 300 Kelvin, you want to put in one place. It's very easy, you can put it there. And or some flux condition, if you want to give like some watt per second or something, you can put it there. That's easy. But if it is like some complex boundary condition, like for example, I'm using for my lung, I'm using like a very realistic breathing pattern. Okay, it is not a sine function, but it looks like a sine function. So we have a profile for this. So how to use in India? It is very tough. You cannot directly put it there. So then you have to write a user-defined function. Okay, and that user-defined function you cannot use like your own language. So you have to rely on how Fluent is built on. Okay, so Fluent has some built-in things, some macro. So you have to use some of this to write down the these things. But they have a guide for that, how to write the user-defined function. So if you have like a complex kind of problem, you have to work on it. Especially the Fluent is given the main scheme. Okay, generally when we use our own coding, the main scheme we generally don't touch the main scheme. Okay, we touch some other subroutine. Okay, where you need to change. So these kind of things we have to write a user-defined function, means it is another subroutine. We have to attach to it. And there are some other things like, for example, if you want some heat generation somewhere inside the domain, we have to write that on as well. So it is not very like a click, put and get the results. It's not so easy. If your problem is complex, you have to deal with it that way. So these are the tabs. Okay. So this is you calculate the run calculator, it start running it. So these tabs allow you to describe your problems, physics and control your simulation. For this course, our current objective is to be familiar with these tabs, so that will show you, know the details about them and use them for a successful simulation. Okay. I'm just going very briefly. So here we have another thing is like beginning of the Fluent. Okay, we have this kind of things, the mesh. So you can check the mesh, click the check, and then it will give you all the mesh information. Okay, so there you can check it, and or you can display and you can see how the mesh looks like. And the solver. So do you want to use the pressure based solver or density based solver? So it actually depends. So if it is like a high Mach number flow, or like where the density change, so you need to use the density based solver. Otherwise, mostly we use pressure based solver. Okay, and the velocity formulation is absolute or relative, so we need to check it. And the time, are you solving for the steady state problem or the unsteady or the transient problem? That means del u del x of t, you are solving it or not? Because as I told you yesterday, that most of the things in nature is steady state. Okay, so if you want to use that one, just use the steady. Or if you want to see the development of the flow or development of something from the beginning, you should use the transient one. And transient one is more complex and it needs a lot of time and also some analytical ability. Okay, and the 2D space, if you have like 2D problem, is it the axisymmetric case or planar case or this one? So you have to choose from here, just stick it there. And the gravity, do you need the gravity or not? Is your problem is related to some gravity? For example, if you want to solve some natural convection, okay, in natural convection there is no external force. Like if you hit one surface, that heat can conduct through the wall and come inside and then hit the air, and air actually start to rise. So that is called the buoyancy. So that we have to give the gravity turn on. Even in our lung problem, we have to use the gravity, because the particle deposition sometimes is due to gravity. Okay, it goes, if it is heavier, it goes that way. So we have to take it. But in some like microfluidics cases, Generally, they don't use gravity because the gravity is neglected. It's very small cases. You don't need it. So already I discussed, so I don't need to go this on. Now here this is very important. What equations you are actually going to solve? So there are a lot of equations here. The Professor Chakraborty already mentioned this morning. You can see the multi-phase. Your problem is multi-phase or single phase. So you have to check it before you start. Okay. So we are not dealing multi-phase here. We are dealing the single phase. So that's op. Op means it is not activated for your problem. Now energy. Are you solving any temperature related problem? If it is, just double click and it will be on. Okay. And now viscous. Is it a laminar flow or turbulent flow? So that is what I said. You need some experience. Okay. So what kind of flow behavior you are expecting from this problem? Okay. If it is or there are some free calculation. For example, for a pipe flow, you already know that if the Reynolds number is less than 2000 or 2300, so it is a laminar flow. So you can easily choose this viscous or laminar. Or if it is more than 4000, it is a turbulent flow. Then you can use viscous. There are some turbulent modeling. So in turbulent flow, there are a lot of models. Okay, there are LES, there are K epsilon, A omega, lot of things. So you can actually choose one of them from here. Okay, and then radiation is your problem related to any radiation? Then you have to turn it on. And radiation has also 4 different kinds of radiation. Okay, surface to surface. So those kind of things. So you can choose which one is appropriate for your model. So that means you need some understanding before you solve a problem. It is not like you ticked one and get the results. Okay, you should have some knowledge beforehand. Which one will give you good results? Are you using the heat exchanger? You have to tick it on. Or are you solving any species, any concentration related problem like a diffusion problem? You have to tick this on. Are you solving any discrete phase, or you are doing any solidification or melting? So my group is working on phase material. So phase material means is a solid phase and then is becoming liquid when the temperature comes. Okay. So this time we need to turn on the solidification and melting. Okay. Mostly it is called a thermodynamics problem. And acoustics, are you doing it or not? So those are very important, and you have to check. All equations are different. So which equations you are going to solve. And the good thing is that if you install the Ansys properly, everywhere in the bottom there is called help. If you click the help, it will show you all the explanation on everything. The things I already mentioned here. Everything is there, and there are some recommendation. Okay, which one is for what? So if you print it out, it will be like this kind of thick book. Okay. So it is good that it is already in there, and it is like web based, or there are some PDF as well. So you can have a look. Okay, I already mentioned this. Now the models. Which models you want to use? The viscous, I already have told you. Now the material properties. Okay. So which material you are going to use? So in Ansys model, we have a library of materials. Okay, you can choose from there. Or if you know your own properties, you can also just select something like air and click on it and change the properties according to your data. That okay. So name doesn't matter. So you can actually do it. So this material property, you need the accurate material property, because I think here most of you are engineer, right? So engineer, they are very strict about the dimension and the property. I know it. I'm not engineering background, but I know engineer, they are very strict with the dimension and the material property. But as a scientist, they don't care about that. Okay, scientists, they care about some parameters like the Reynolds number, Prandtl number, Rayleigh number. So those kind of things actually generalized. Okay, all the dimension, all the parameters is going into that. So now it doesn't matter is a very big room or a small room. If you just set of the parameter this, that actually represent everything. Okay, so this is the difference between the engineer and the scientist. So they make like this way. Okay, here we have like a cell zone. So you can check how many cell in your how many zones in your system, and this is the way you have to identify. Now the boundary condition. As I told you, boundary condition you can have. So generally we have here the inlet, the outlet, and the wall condition, and the interior surface is nothing. Just put it there. So this wall boundary condition. So that means the wall is like a no silly boundary condition. That is the general. That is wall is the moving. But in some places we just move the wall. Okay. So there are some way that you can specify the velocity on the wall. The wall can move. Also the inlet, you can put in the inlet, you can put like a velocity inlet. You can use like what I call is mass flow rate. Okay, so anything you can put it there, and also apply the UDF, the user defined function. If your input inlet condition is complex, you have to write your own. So the boundary condition I already mentioned. In the general pressure inlet, pressure outlet. Pressure outlet is mostly like an open condition. For example, in your lung, we have like a 23 generation, but we can't actually get 23. We get about 15 to 17 generation. So after that, we just cut it and put it like a outlet condition. So that means it's free. The particle and air can freely go. Okay, that's why it does not affect your anything. It's an open condition. We call it open boundary condition. In COMSOL, they call it open boundary condition. In Ansys Fluent, they call it pressure outlet condition. Okay. Now for incompressible, because it's a compressible, incompressible, we have the velocity inlet and the outflow. Yeah, like for compressible, we have mass flow rate, mass flow inlet or pressure far field. For other wall, we have symmetry. Okay. So if your flow is symmetrical, for example, like an attic shape building. Okay. Attic shape building, the building roof is like that. So initially it is thought that the flow is symmetric. So the streamline like that is a half of this the same. This one is the mirror image of that one. So in that case, they did not solve the whole triangular shape. They put the half of the triangular. Okay, right angle triangle. Normally they solve this one, but later on they found that no, this is not right. So sometimes the flow actually changes. Is not symmetric. But yeah, this kind of symmetric condition, you can use the symmetric boundary condition, axis boundary condition, or some periodic. If like comes every interval the same results, you can apply the periodic boundary condition. Okay, and it will be the same. Some special is called the inlet or outlet vent, intake or exhaust fan. This kind of boundary condition you can apply. And the internal one, you can use some fan. Okay, we just do for the mixing. We use the fan internally. Some interior condition, you need to do anything in there. Some porous jam, radiator, wall. So this kind of condition. This boundary condition, velocity inlet, you already have mentioned. I don't want to mention anymore. So pressure outlet, all boundaries. Okay. And dynamic mesh, sometimes we need to like, it is especially used for fluid extraction interaction. Okay, we need a moving mesh. For example, something is moving that way, and we know that close to this solid one is very sensitive. So we need to give like a very dense mesh near the solid wall. Okay, so that's why if we move that way, and if your mesh is here, the highest mesh, it doesn't work. So that's why mesh should also move with this geometry. Okay, that's why we need a moving mesh. But in your case, we are not showing it. And the reference value. So reference value does not do anything with your simulation, but actually it helps you for the post processing. Okay, post processing means, for example, when you calculate the Nusselt number or the heat transfer rate. Okay. So in that case, you need a reference temperature. So if your reference temperature is not correct, which reference temperature you are calculating your Nusselt number, then you will not get correct results. So for example, if it is a time dependent one, okay, from 1 to 10 seconds, and you want to get a curve, and then every time step it is calculating the Nusselt number, but if the temperature is not correct, it is not giving you the correct solution. Okay. So that's why it is also, the reference value is also important for your post processing. It does not do anything with your results, with your simulation. I think that's it. And solution method. Okay, yeah, sorry, we forgot the solution method. Yeah, here we mentioned that for solution method, we have the pressure velocity coupling. Okay, so you see the pressure velocity coupling in the momentum equation. You see the pressure on the right side minus 1 by rho del P del X. So that is called the pressure gradient. So that one, we there are scheme, we use simple scheme. There are some simple leg, there are some Picho or something. There are a lot of scheme there. So you have to select which one you want. And then for the special discretization, we have least square cell based, okay, or you can use like the quick scheme, okay, or second order upwind or first order. First order is very, very simple. So for the pressure discretization, for momentum discretization, it is the default is second order upwind, but you can use like the quick scheme as well. QUICK, quick scheme. So the simple method is very popular and widely used. So we'll use here this simple method, and coupled method is also popular and helps in convergence. Yeah, so if simple one is giving you divergence your results, choose the couple one. Okay, so you can choose one of these. Now these are the things yesterday Professor Chakraborty told about your the relaxation factor, okay, for your quick convergency. So these are the important things for pressure term, for the density, for body force, and for momentum. So these are the value. One is default. So that means the density and body force does not actually interfere for your convergency. But the most problem is the pressure, the continuity equation. Okay. So you can see the white line. It does not come down your residual. So we normally set up some residual value. The default value is 10 to the power minus 3. But if you make it smaller, 10 to the power minus 5 or something, you can see the pressure or the continuity equation is not coming down. It takes long time to come down. Or sometimes it does not come down, goes up. So diverge your solution. So that's why you see very small value, use 0.3. Okay, we just generally do it. And if you put too much small, it takes long time. But we don't know, we have to just try. So this is the default value. If your solution doesn't converge, just try to reduce it. Okay, and you can try it. Generally, these are the default value. Yeah, this is the residual. So generally for continuity, x velocity, y velocity, energy, everything, the default value is 10 to the power minus 3. But here you can see 10 to the minus 6. So it's up to you how much accurate you see your result. But remember, if you give more value, smaller this, it takes longer time for the simulation. Okay. What else here? Yeah, and what you want to see on the screen on the left side, you can tick print to the console. That means in the bottom they can just print it, and plot means if you tick the plot, they will show graphically. So the solution control, these are the things I already told you. Yeah, initialization. So you have to give some initial value, and every time you run a simulation, you have to do the initialization. There are two ways of doing the initialization. One is called the standard initialization. You put all the values, and another called the hybrid initialization. You don't need to do it, just click it. It will actually do it all together, initialize your system, and then start the simulation. And calculation activity, here if you want to do some animation at the end, so you have to like modify how you want to save the data. Okay. So if it is a time dependent problem, then maybe after every 50 time step or 10 time step or 100 time step, you want to save your data, and at the end you can create the animation. You see how the fluid is flowing, you can see at the end. So this is the place where you can specify how many, because you cannot save the data for every time step. If your time step is thousands or hundreds of thousands, you cannot do that. It will take lot of space. Okay, but this is the way you just find out some reasonable number, and that's the way you just do it. And then run the calculation. So for a steady state problem, you only need to give the number of iteration, how many iteration you want. Okay. So for example, we just give 1000 iteration, and you found that the solution does not converge. Does not converge means it is not coming down the residual value. We already set up the residual value, and you can see it is coming up to here and 1000 finished. So you can increase the number again and click. Don't click the initialization again, then you will start from the beginning. Okay. So you can increase 1000 again, and you can see it's coming down, and after a certain time it's just finished. And then you give the converge solution, and then you can do the post processing. Yeah. After that is the post processing, and we will show you how to do the post processing. Okay. This is a CFD post. Okay. So you just click on the results. Solution already did. Click the results, and then it will go the CFD post. That's it. Thank you. Do you have any question?